From HanselMinutes.com, it's Hansel Minutes, a weekly discussion with web developer and technologist Scott Hanselman. This is Lawrence Ryan announcing show number 411, recorded live Thursday, February 13th, 2014. This episode of Hansel Minutes is brought to you by Telerik, offering the best in developer tools and support. Online at telerik.com. And by Franklins.net, makers of Gesture Pack, a powerful gesture recording and recognition system for Microsoft Connect for Windows developers. Details at gesturepak.com. In this episode, Scott talks to James Friend, author of PCE.js, which is a port of PCE, the portable computer emulator.
Hi, this is Scott Hanselman. This is another episode of Hansel Minutes, and I'm talking with James Friend, and he has a website at jamesfriend.com.au, and he has made a port of the PCE emulator. PCE.js is his port, and I'm actually looking at a Mac Plus emulator in my browser. You've made not just this emulator, but a number of emulators, haven't you, James?
Yep.
And you seem very casual about that, like, oh yeah, you know, you're just over here emulating the IBM PC in a browser, no problem. That's amazing. Do you think that's amazing?
I think it's amazing that it can be done, for sure. I think it's amazing that the web platform has gotten to the point where we can make these things run in the browser across different hardware and different operating systems.
And this isn't faked. I think we've seen lots of things where we'll have JavaScript and HTML, and someone will make a Windows interface or a Mac interface, and it'll look and feel like it, but it's not really it. This is really emulating the CPU. This is pretending to be a 68,000 emulator, a 68,000 processor. The Mac doesn't know that it got booted up inside a browser.
Right. So basically, yeah, it's just loading the original startup code, the original 68K machine code, and it thinks it's got a 68K processor and the amount of RAM that was in the original Mac Plus and the same input and output devices, and it's just running as if it's a real Mac Plus.
Mm-hmm. And so, like you said, the ROM is totally unmodified.
Yeah, except the emulator itself does patch the ROM slightly so that it intercepts when the computer tries to access the floppy drive. So that basically floppy drives, I think they required a bit of delicate, timing that had to be quite precise to do with the way the disk spins and stuff. So the emulator itself actually, the original emulator, the part that was written by the original author, not myself, a really impressive guy called, I think it's Hamper Hug, the guy who wrote the PC emulator originally. It basically overwrites some of the Mac Plus's ROM with just a little bit of code to tell the emulator, hey, we're using the disk now, like jump out of the emulated code, jump out of the real Mac OS and into the emulator so we can do some disk input and output.
So the original emulator, and there's millions of, not millions, but there's hundreds of emulators out there. It seems like if you're into computer science at some point, you're going to write an emulator of some kind. And Hampa Hug wrote a thing called PCE.
Yep.
And he's got an Atari ST, an IBM PC, a Mac Plus. So he's not just emulating 68,000s, but also 8086, 8186. And of course, since the Atari ST was a 68,000, it's using the same part of his emulator that it uses for the Mac.
I think he added 68010 as well for that.
And this is written in what? Idiomatic C or C++ or what?
So, in fact, the main reason that I chose this particular emulator project, because in some ways it's not well known the way that, say, VMac, Mini VMac is probably the most widely used and well known classic Mac emulator. But this code of PC is so absolutely clean and easy to understand, the way that it just has very careful responsibility of ownership of various bits of state. There's basically just a big structure that describes the current state of the CPU and a structure that describes the current state of the system, and then they just get passed through really easy to understand and well broken down functions. So, in fact, the fact that it was this really straightforward code to a person who's looked at a few emulator code bases, and that it was just pure C, there was no assembly, was critical to me being able to pull this off. I see. Yeah, for example, if there was assembly in there, I couldn't have ported it to the browser because the way that I ported it was using emscripten, which can compile C and C++ to the LLVM intermediate representation and then convert that to JavaScript. So it has to be high-level code that's not tied to a particular architecture.
So it's interesting that you're saying that the C, which I think most of us think of as being low-level code, has to be sufficiently high-level enough for it to move over to emscripten and the LLVM system.
Right. Well, I mean, C was, to a lot of people, the original portable language. You know, that was what was great about C when it first came out, because at the time people were still writing things in, you know, like the assembler for the PDP-10 or whatever, or the assembler for various different completely separate computer architectures. And C was this code, this language that could be compiled to all of those architectures. And to us now, that just sounds like, well, of course, you know, if you're going to support a certain language on a certain platform, it needs to compile to it. But at the time, that was, you know, the original portable language. So it has to be, portable C. Can't do really crazy stuff with like casting values to completely different types that will then potentially rely on some thing that happens only on certain architectures. For example, only works on an architecture where an int is worth this, you know, this size or whatever.
Right.
So in that way, it has to be portable to be able to be compiled by emscripten. And PC satisfied that.
Did emscripten do what you needed it to do? Is it just a matter of, I'm not going to use GCC, I'll use emscripten and I'll run it through, and then this low-level virtual machine stuff will pop out the other side? Or did you have to modify emscripten?
Well, in the core of what it does, emscripten is quite relatively easy to use for someone who's, you know, both familiar with the traditional GCC make kind of toolchain of compiling C applications, and also familiar with JavaScript and a lot of JavaScript tools. But basically, it does have a drop-in replacement for make and configure. However, that's not really going to guarantee that your code's going to build or work properly, especially considering that, you know, on a particular system, you might have lots of different libraries installed. A really common one these days is SDL, which is a really useful library for abstracting input and output. That is keyboard, mouse, drawing to the screen, sound. So you can just write your application against SDL, and it'll ideally work on any platform that supports SDL, whether it's like Mac, Windows, Linux. And
SDL is the simple direct media layer?
Yep. So that was a really handy tool for people doing games and emulators and things like that it's been around for a few years. So that's something that someone might have installed on their computer, but in the browser, we can't really access any code other than what we've loaded ourselves. So things like SDL have to actually be included with the code that's being built for the browser. But actually, what emscripten have done have sort of re-implemented SDL. So in terms of things like canvas, so rather than drawing to the screen, it draws to a canvas, and rather than outputting audio to whatever your output device is, I guess on Linux it's like dev sound or whatever it is. In the browser, it might output as HTML5 web audio data API or audio tag or whatever.
Okay, so to hang on though, to put this in the information for the audience who may not have all of this. So if you're saying, if I understand correctly, like what people usually think of when they think of SDL, the simple direct media layer, is it's this layer that lets you get access to your audio, your keyboard, your joystick, and then underneath it is usually either OpenGL or Direct3D. And you're saying on the side of emscripten, which takes the LLVM bytecode and turns it into JavaScript, they have put Canvas underneath that and HTML5 audio, where we would ordinarily expect to see OpenGL or Direct3D. Is that correct?
Yeah. So basically, emscripten comes with a bunch of re-implementations of various popular libraries. So there's SDL, there's some OpenGL tools, some different kind of I/O tools like X11, and it's got these little JavaScript implementations of those things in terms of the tools we've got in the browser. So Canvas for graphics, for outputting a display, and Web Audio API for audio, and just mouse events. For example, it can take mouse and keyboard events and turn those into SDL key presses and mouse events in SDL's own representations of those things. So code that's already been built to use SDL for its keyboard and mouse input, for example, should just work when compiled with emscripten, and it really does a lot to make it easy to rebuild those code bases in the browser.
Okay, so you take the portable C from PCE, the original C version of PCE, and you use LLVM GCC, or you use Clang, and then LLVM pops out the other side, and then you take that, and that turns into JavaScript. Right,
so that's the core part of emscripten, apart from the fact that emscripten has all these nice tools to, basically drop in place of GCC, for example. It has something called emcc, but that's really just a wrapper around GCC Clang. But then with that output, which is what's called LLVM intermediate representation, which is kind of like LLVM bytecode, I guess. It takes the emscripten compiler takes that and converts it into, first, I think, naive JavaScript, and then it has, like an exact representation of an exact kind of JavaScript replica of the LLVM bytecode. And then it takes that and tries to optimize it so that it's not a huge, huge block of code. It does end up still being fairly large amount of code, but because there's a lot of redundancy, once you actually load it in the browser, various magic that we all benefit from every day, like gzip compression, turns that into something that's manageable. So the output is basically this JavaScript code, which only deals in values, like it only deals in numbers.
Right.
And it's got a big typed array, which is a feature that's been added in HTML5 to JavaScript, which basically allows to have an array of just raw data that you can look at as different kind of types, like an 8-bit int, and so that's like the memory that this application has access to. Just like in native code, you would have like a big chunk of memory that your application can use, and so that all that comes together to basically run kind of something like that LLVM intermediate representation in your browser as JavaScript.
How much do you have to change the resulting C? How much of this is bringing libraries together and making a build system versus actually having to go in and patch, in this case, Hampa Hug's original C code? Because I'm looking at the history in your GitHub here, and it seems like you are having to poke around and change things at the C level that will then affect how your JavaScript emulator runs.
Right, and so that's kind of why, to be able to do this project, I needed to have, as well as a good understanding of emulators and how they tend to be written, and a good understanding of how JavaScript runs in the browser, and what the nature of the browser environment is for code. I also had to, be fairly solid on my C. I actually went through Zed Shaw's Learn C the Hard Way, just to make sure that I was like boned up on my C before diving into making lots of changes to this code base. But I think in the end, the changes end up being fairly precise. I mean, some of them will have a comment above that says this is a bit of a hack. Like, for example, to get the mouse working the way that looks really, really nice for users and the way that people expect from using, say, VMware or whatever, basically you need the mouse to just go wherever they've got the mouse hovering over the window. Whereas a lot of emulators require to actually take control of the mouse, and so you have to click on them and then that captured your mouse. I was basically doing this kind of neat or gross hack, depending on your perspective.
Well, according to line 439 of Command 68K, it actually says gross hacks to set mouse position in browser. So it sounds like you felt it was gross at the time.
Yeah, and it's certainly gross in terms of what it's doing is getting the mouse position from the browser in terms of the browser, actually through the stubbed out SDL code. So it's using an SDL method, which emscripten is then implemented in terms of mouse events, or to basically get the position of the mouse relative to the canvas, and then it's like converting that into and poking into memory the values in the actual emulated macOS of where the mouse position is. So in the emulated macOS code, it's running. There will be some routine where it updates the mouse position. And basically there's a certain location in memory which made this quite easy because in the original macOS they had these things called low memory globals, which are just a bunch of global variables for the whole operating system, and one of them is like the mouse position. And so I was able to poke the value of the mouse X and Y coordinates straight into macOS memory, which is something you couldn't do on a modern operating system because of all the layers of indirection and protection of memory.
That seems simple. Like when you're like, I just kind of poke this into memory. I'm looking at the code here though, and it seems pretty specific. I mean, it's basically magic numbers. You're going and saying, take this, 16-bit integer, and here's the mouse Y, and then you're basically shoving it into 3 separate locations. Yep. How in the world would you know those locations? How would you figure that out?
Well, fortunately, some people have gone to the effort of figuring out what all these low memory global variables are for the original macOS. I found some document on the website of, I think it's like a Linux distro that someone made for 68K Motorola processors. So a Linux distro that could run on the original Mac, although probably many years after the fact. And so they documented all these magic locations that you can put things like mouse position. I think there probably would be a nicer way to have implemented it, like this way that the floppy drive works in PCE is it actually just once the operating system tries to access the floppy drive, PCE just kind of traps that and says, all right, well, we'll just actually do something else, like go onto the system's hard drive and grab out the floppy disk image. But that would be a lot more complicated because it actually involves writing some 68K assembly code, kind of like a little custom driver, and injecting that into the emulated macOS. So what I did was a lot simpler, just poking in values where macOS is going to look for the mouse position. But it seems to work pretty well.
It works pretty clearly. I wonder, though, when you're putting together an emulator like this, I feel like there must be a moment or a number of moments or a long time actually before anything actually happens when you're just trying to get this thing to start up and you're kind of feeling around in the dark. And then if a bug like this came along where you didn't like the way the mouse was behaving, I think maybe myself and maybe people that are listening would just kind of give up. You're like, heck if I know. I'm amazed the thing works at all.
Yeah, and to be honest, I wasn't really sure if this was even going to be possible when I started. I had this idea, a sort of a rough feel of, what can be done in the browser, the other previous emulator in the browser projects that people have done, like, there's like an Apple II in the browser, and I can't remember what the one really I saw that made me think that I could do this, but I think probably Fabrice Ballard's x86 emulator in the browser, which he actually wrote, from scratch. It's JavaScript from scratch, emulating an x86 CPU. And when that came out, everyone was just, on Hacker News, everyone was just amazed that this could be done. And I think once I saw that, I figured, if you can do that, an x86 CPU emulator, then I think this can be done. So once I got past that point of at least having some confidence about it and seeing what people were achieving with emscripten as well, in terms of being able to compile existing code bases like the Unreal Engine demo, I think it's called Epic Citadel.
Yep.
Which has successfully compiled, the Unreal game engine to run in the browser under emscripten at perfectly acceptable frame rate. So I felt like this was doable, but then I had to find an emulator code base that was understandable to me and to the degree that I needed to be able to actually get things working, and I found that in PCE. And then from there on, it was just a lot of trying to get it to build, looking at the errors spewing out of emscripten's wrapper for GCC LLVM, and then slowly one by one going through and trying to figure out what it was complaining about, and then it got to the browser. Something was running in the browser, but there's no visual output. I couldn't really tell if it was working or not, because an emulator can run without a screen, without any input. It's just a emulated computer, so it can be running along and churning through instructions, and so you have to really kind of have a bit more visibility of what it's doing. So I looked at what the emulated CPU was doing, where it was moving through the macOS code. And even then, it's possible that it sort of it's churning through it, but it doesn't really understand what's happening. But I was able to follow it moving through the code in the way that, according to the comments that some people have nicely provided for the macOS ROM, indicated where it should be going. And then from there, I could tell that things were kind of working. And I looked at, okay, so PCE outputs the display through SDL, but it's not working yet. But I was able to kind of see in memory the in-memory representation of what's on the display. So I could tell that there was a bunch of there was a byte of one of because the macOS boot screen was originally this kind of black and white grid. So one black pixel, one white pixel, one black pixel, one white pixel, and so I could see that in memory.
And are you saying you can see that in F12 tools? You're seeing this in JavaScript in a byte array?
No. It's actually in the C, the within the memory that emscripten has. So emscripten is kind of another level on top of that. It's it's got this typed array that represents the memory that's available to emscripten, and then inside that you've got your C code running. So I was able to kind of edit the C code of PCE to dump out what was in its sort of frame buffer, its screen, its emulated screen, and then so I came to the realization that I was running into the problem that every emscripten ported application has, which is that the browser can't just run code indefinitely. It can't just keep running a piece of code that never stops and yields back to the browser. That's what happens when you see those error messages that say an unresponsive script is running on the page.
That's the browser detecting that an infinite loop is just this has been going for 20 seconds and it never seems like it's going to stop.
Right, and that's because the way that JavaScript code runs in the browser, it does have to regularly yield back to the browser's main event loop so that the browser can do other things like update the screen, update the display of the page within the browser window. So I had to find a way to take this program that was designed, as most emulators are, to just run infinitely in an infinite loop. I had to break that up into little manageable bite-sized chunks for the browser. And so I was able to do that by basically going into the main loop of the emulator. Most emulators have this main loop that just updates a few things and then runs some CPU cycles and then loops around.
Mm-hmm.
And I was basically able to break that up to, say, only run a few, say, 10,000 cycles of the CPU and then stop. And then the browser basically does kind of like a set timeout to say, as soon as you've finished doing other things, add into the schedule to run another of those batches of 10,000 CPU cycles. So once that was happening, a whole lot of other stuff started magically working, like the output to the log of the emulator, which is kind of like the standard output in C, started spewing out all these log messages. Because up until that point, this infinite loop was blocking the browser from actually updating, anything else on the page, not just the screen, but not just the emulator screen, but just the log saying, the emulator's managed to load this disk image, it's managed to start the CPU, it's allocated this much emulator memory. And so once I saw that, I was like, well, things are working. And from there, it wasn't much to just figure out how to actually get the display appearing in the canvas. And it was just a matter of the fact that PCE only outputs RGB, so like 8 bits of red, 8 bits of green, 8 bits of blue.
Right.
Whereas Canvas typically expects RGBA, so it expects an extra alpha channel.
Right.
And so when I was copying, I just had to add like a little bit of extra code to emscripten so that when copying the kind of the frame buffer from the emulated memory, so like the Mac computer is like, it's drawn the screen into its emulated memory. It's like, okay, so this is what's on the screen. And normally in a real computer, the video card or whatever would grab that from memory and put it out on the display. The emulator kind of does the same thing. It just grabs what's in the Mac's memory in the frame buffer and outputs it via STL to the STL window. So basically, in the process of doing that, I just had to convert it from RGB to RGBA by just adding a full fully opacite value for each pixel for its alpha channel. So you end up with an 8888 RGBA output. So that's 8 bits for each channel and the alpha channel. And then magically it was appearing in the canvas. I'd only been working on it for, several weeks at that point. So it was quite fortunate that I did this project when I had a lot of free time in between jobs. And when I got to that point, I felt like I hadn't been wasting my time for all that time that, in between getting a new job, I had done something that, I thought was really neat. And it was really gratifying to see that finally coming out on the display, that little happy Mac face that you get when you boot up the classic Mac OS.
That must have been like the moment where you just jumped up and cheered.
Yeah, absolutely. I was actually staying with my mom over in Melbourne. I'd just been visiting her for a couple of weeks because I thought I'd take the opportunity after quitting my last job to have a bit of a break from my life in Perth. I was over there sitting in my mom's living room on my laptop, and just it was just really, really gratifying to finally see that working and booting straight up into macOS without any problems, and being able to click on Macintosh HD and browse around and use simple text, and I'd loaded it up with Mac Paint as well. And just keep using all of those old programs that I'd used when I was a little kid on my mom's classic Macintosh.
Why do you think it's important for people to do these kinds of exercises? I mean, there's certainly the intellectual work, and there's the OG. That's amazing. But is there historical significance for for putting these together?
Yeah, absolutely. I think that that it's very important that we preserve all of the history of personal computers and all the different stages that they've gone through and everything that's been built to get to the point that we're at now. And I think that there is a risk of that being lost because, in the short term, that's just an old computer. It's obsolete, and people, don't want to waste their time with some obsolete technology. But then it passes that point and it becomes historical, and it becomes something that's different enough from what we have now that it's worth looking at and seeing how we got here. And in some ways, what's most impressive about looking at the classic 1984 Mac OS is not how old and different it is, but actually how really similar it is to the way things still are on desktop computers, with the Windows icons, mouse pointer, and all of that stuff. So I think for really seeing both how far we've come, but also how long these ideas have been around and kind of shaping the way we use technology, I think it's really important to preserve that, and then also to make it accessible to everyone, because emulators typically are not particularly accessible software. They're usually made by fairly smart, fairly geeky people who are happy to dive into a command line. But I think there's a value to making this stuff available to everyone, and so that means putting it on the web, because the web is really the platform that's available to everyone. It doesn't require you to download and install something and fight your way through some complicated command line interface or anything like that. It's just you go to a web page and it's there. And I think that's really the kind of beauty of this, what this embodies, this project.
Do you think you're going to take it anywhere farther, or are you pretty much done at this point?
I have keep getting a lot of emails from people who want to be able to upload their own software and stuff to be able to try out, for example, an old app that they've got on disk somewhere, or, for example, a really popular use case is HyperCard. A lot of people really loved HyperCard. It was a really cool tool that Apple released for building applications, simple applications for non-programmers. And so it's still got a lot of people who have very fond memories of it, and a lot of complex little things were built in HyperCard. I think Myst, the really classic computer game, was originally built in HyperCard. And certainly its predecessors, this game called Spelunks, and another one called The Manhole.
I remember The Manhole.
Yeah, and so that was HyperCard. And a lot of people want to be able to try out their old HyperCard stacks that they've made themselves or that they've got on a disk somewhere. So I kind of want to get that working. Just so that people can open their own HyperCard stacks. Apart from that, I think I'd like to try and tackle another emulator. That's a pretty big thing to be taking on, but I'd really like to get perhaps QEMU working, because QEMU is an emulator that covers a lot of different architectures. I think that one is probably the one that's most likely to be useful for a lot of different applications. And one thing I think would be really cool would be to get Next Step running in the browser.
Oh,
and
wow.
So that's the operating system that was developed by the company that Steve Jobs founded after he got kicked out of Apple. It went on to become the basis for modern day macOS, but also it was the operating system on which the original web browser and web server were developed. So I think it would be really neat to get the original web browser running in a web browser. Only just because it sounds ridiculous, but also because I think it's worth seeing. If you're really technically minded now, you can get it working in VMware if you can find a copy of Next Step. But to be able to show that to everyone, I think would be valuable.
That's very cool. Well, people can check out your site at jamesfriend.com.au, and I'll put links to your blog, your article on why porting emulators to the browser matters, and people can check out PCE.js, both on your site and on GitHub. Thanks for chatting with me today.
Thanks for having me.
This has been another episode of Hansel Minutes, and we'll see you again next week.